Tonight, we're settling in to follow one of the quietly astonishing journeys in human history. Back in 1977, two small spacecraft left Earth on what was supposed to be a tidy 5-year assignment, a close look at Jupiter and Saturn. And yet, here they are, nearly 50 years on, still humming along, still sending signals home from billions of miles past the finish line anyone expected. When they finally reached what should have been the edge of everything familiar, they found something worth sitting with. The true boundary sat 2.4 billion miles farther out than any scientist had calculated. Its shape wasn't the tidy sphere everyone had drawn. The magnetic field twisted in ways nobody had modelled. And the region just beyond it behaved nothing like the textbooks promised. 7 separate discoveries, each one gently dismantling what we thought we understood about our own cosmic doorstep. By the time we drift off tonight, we'll have traced how a pair of spacecraft built with technology from the early 1970s ended up rewriting the map of where our solar system quietly gives way to the space between the stars. And before we start, if this kind of slow cosmic wandering is something you enjoy, a like or a subscribe helps this little channel find its way to more curious minds like yours. No rush about it, just something to consider. Now, let's begin. Picture the year 1977. NASA is preparing to launch 2 nearly identical spacecraft on a mission everyone assumes will wrap up within 5 years. Voyager 2 goes first, lifting off from Cape Canaveral on August 20th. Voyager 1 follows just over 2 weeks later, on September 5th, but takes a quicker path that gets it to Jupiter and Saturn ahead of its twin. That's the quiet joke buried in the naming. Voyager 1 arrives first, even though it launched second. Each spacecraft weighs in at 1,820 pounds and stands about 12 feet tall, carrying a careful collection of instruments meant to study the 2 largest planets in our solar system. The mission carries the name Grand Tour, and it exists because of a planetary alignment so rare it happens only once every 176 years. That alignment lets the spacecraft borrow momentum from each world they pass, slingshotting onward toward the next, making it possible to visit all 4 outer giants, Jupiter, Saturn, Uranus, and Neptune, in a single unbroken journey. Without that fortunate lineup of planets, reaching all 4 would have demanded separate missions and far more fuel than any rocket of the era could have carried. The planets simply lined up, and NASA quietly took the opening. The plan, on paper, was modest. 5 years of close study at Jupiter and Saturn, and then a slow drift into the emptiness beyond, as the power dwindled and the instruments, one by one, fell silent. Nobody expected these machines to outlive their warranty by much. Certainly nobody predicted they'd still be working in 2026, closing in on half a century of service. And absolutely nobody guessed that their most remarkable discoveries wouldn't come from the planets at all, but from the strange, quiet frontier that lay far beyond them, a boundary scientists were confident they already understood. So let's sit with what scientists in 1977 actually believed about the age of the solar system. They already knew the sun was constantly breathing outward, releasing a steady stream of charged particles known as the solar wind. This wind pushes outward in every direction at somewhere between 250 and 500 kilometers per second. It's a plasma, really, a scalding mixture of protons and electrons, hot enough to strip atoms down to their bare components. The solar wind itself came to light in the late 1950s and early 1960s. A physicist named Eugene Parker, working at the University of Chicago, predicted it existed purely through theoretical reasoning. He recognized that the sun's corona, its outermost atmospheric layer, runs so hot that gravity simply can't hold it in place. The gas has nowhere to go but outward. Continuously, Parker's idea wasn't welcomed warmly at first. Some scientists assumed the solar wind would only appear briefly during solar storms. But measurements taken by spacecraft in the early 1960s proved otherwise. The wind never stops. Every day, every year, no matter how active or quiet the sun happens to be, our star is steadily shedding mass through this outward flow at a rate of roughly 1 million tons every second. That number sounds enormous, and yet the sun is so vast that even at this pace it would need trillions of years to lose any meaningful fraction of its total mass. Still, that wind has to run into something eventually. It can't simply expand forever into nothing. The space between stars isn't truly empty. There's gas out there, remarkably thin, but present nonetheless about 1/10 of an atom in every cubic centimetre. For comparison, the air at Earth's sea level holds about 10 to the 19th atoms in that same tiny volume. Interstellar space, in other words, is roughly 10 quintillion times less crowded than the air around us right now. It's a more perfect vacuum than anything we've managed to build in our finest laboratories. And yet, it isn't nothing. Across distances this vast, even gas this faint carries real mass, real pressure, real momentum. That interstellar material is also in motion, though not because it has any current of its own. It moves relative to us because our entire solar system is moving through it, orbiting the galaxy's center at roughly 137 kilometers per second, something like 490,000 miles per hour. From the sun's point of view, the interstellar medium behaves like a headwind streaming past at exactly that speed. And wherever the outward push of the solar wind meets that quiet headwind, a boundary forms. Scientists gave it a name: the heliopause. This is the place where the sun's authority ends and true interstellar space begins, where the outward pressure of the solar wind finally balances the inward pressure of the galaxy's gas. Beyond that line lies a very different kind of space, one shaped not by our star but by the wider galaxy, where cosmic rays roam freely and the galactic magnetic field, not the sun's, calls the shots. By the 1980s and into the 90s, scientists had built increasingly sophisticated computer models of this boundary, running three-dimensional simulations that folded in magnetic fields, plasma behavior, and the sun's own motion through the interstellar gas. These models suggested the heliopause would be more or less spherical, perhaps drawn out slightly like the tail of a comet in the direction opposite the sun's travel, but essentially a tidy, symmetric bubble sitting at a fairly consistent distance in every direction. Their best estimate placed it somewhere between 90 and 100 astronomical units from the sun. 1 astronomical unit, for reference, is the distance from Earth to the sun, roughly 93 million miles. So 90 to 100 AU translated to somewhere between 8.4 and 9.3 billion miles out. Given the data available at the time, that estimate felt entirely reasonable. The models leaned on a few working assumptions that the interstellar medium was fairly uniform in density and pressure, that the sun wasn't barreling through it at any unusual speed, and that the solar wind's output stayed roughly constant. All sensible assumptions, given what could actually be measured in the 1980s and 90s. Scientists knew the solar wind's strength from readings taken near Earth. They estimated the interstellar medium's pressure from what could be observed astronomically. They ran the numbers, and the math kept landing in that same 90 to 100 AU range. That's where Voyager, everyone assumed, would eventually cross. But before even reaching the heliopause, the solar wind was expected to hit something else first, a shock wave known as the termination shock. This happens because the solar wind travels faster than sound can move through its own plasma. It's supersonic. The speed of sound through any gas depends on its temperature and makeup and in the solar wind's plasma. That speed sits somewhere around 30 to 60 kilometers per second, far slower than the wind's own pace of 250 to 500 kilometers per second. So the solar wind is moving somewhere between 5 and 10 times faster than sound can travel through it, technically supermagnetosonic, since magnetic fields also shape how waves move through plasma. Whenever a supersonic flow meets an obstacle, a shock wave forms just ahead of it, the same principle behind a sonic boom from a fast-moving aircraft, just playing out in plasma instead of air. At the termination shock, models predicted the solar wind would abruptly slow from supersonic to subsonic speeds, dropping from roughly 250 to 500 kilometers per second down to somewhere near 50 to 100. The plasma would compress and heat sharply, its density climbing by a factor of 3 or 4, its temperature jumping by an even larger margin. Charged particles caught in that shock would get flung to much higher energies by the electromagnetic fields tangled up in the shock structure itself. Models placed this termination shock somewhere between 75 and 90 AU, a bit closer to the Sun than the heliopause itself, with the exact distance shifting depending on how active the Sun happened to be. During solar maximum, extra solar wind pressure would push the shock farther out. During quieter solar minimums, it would drift back inward. Between the termination shock and the heliopause, models predicted a region called the heliosheath, made up of solar wind plasma that had already been slowed and heated, flowing outward and sideways as it tried to work its way around the obstacle of the interstellar medium. This flow wasn't expected to be gentle. It would be turbulent, tangled with magnetic irregularities and plasma instabilities, but still recognizably made of solar material, particles that had once belonged to the Sun. Scientists expected the heliosheath to stretch somewhere between 10 and 20 AU thick, a broad transition zone bridging the shocked solar wind and true interstellar territory. Beyond the heliopause, galactic cosmic rays were expected to take over entirely. High-energy particles born in distant supernova explosions and other violent events scattered across the galaxy. These particles mostly can't push their way into the inner solar system, held back by the Sun's magnetic field and the solar wind itself, though some do trickle in at reduced intensity. The heliosphere, in effect, acts as a kind of shield, softening or deflecting many cosmic rays before they ever reach the inner planets. But once past the heliopause, models expected their intensity to climb sharply, perhaps doubling or even tripling compared to what we measure near Earth's orbit. The crossing itself was expected to be fairly crisp. A transition, scientists guessed, might take a few weeks or a few months at the outside. Solar wind plasma should vanish suddenly, or at least fall off steeply. Galactic cosmic rays should rise sharply in response. And the magnetic field should visibly shift direction as the spacecraft left the sun's field behind and entered the galaxy's own. The sun's magnetic field within the heliosphere runs mostly outward from the sun in a radial pattern, though twisted and braided by the sun's own rotation. The galactic field, by contrast, was expected to follow the broader architecture of the Milky Way, likely meeting the radial direction from the sun at a noticeably different angle. So at the heliopause, instruments were expected to register all of it at once, plasma fading away, cosmic rays climbing, and the magnetic field swinging around to a new orientation, all unfolding over a matter of weeks to months. Scientists felt genuinely confident in this basic picture. The mathematics of magnetohydrodynamics was well established. Shock physics and plasma behavior had been studied for decades already. The models had been tested and refined over years of careful work. They might be off on the precise distances, sure, but the overall architecture, they assumed, would hold. A termination shock somewhere around 75 to 90 AU, a heliosheath 10 to 20 AU thick, a heliopause near 90 to 100 AU. A clean, reasonably sharp line separating our solar neighborhood from true interstellar space. They were wrong. Not just slightly off, but dramatically so. And that turned out to be merely the opening surprise. To really appreciate how remarkable these discoveries are, it helps to sit for a moment with the technology that made them possible. Because everything Voyager accomplished, it accomplished using equipment designed and assembled in the early 1970s, before personal computers existed, before the internet, before cell phones. The onboard computers are, by today's standards, almost comically limited. Each spacecraft runs 3 separate computer systems working in concert, one handling commands sent from Earth, one processing scientific data, and one managing the spacecraft's orientation and pointing. Together, all 3 systems share roughly 68 kilobytes of memory. A modern smartphone holds millions of times more memory than both Voyagers put together. And yet, engineers back on Earth can still send updated software to these aging machines. In 2002, NASA transmitted new code to Voyager 1 to work around a failing memory chip. In 2013, engineers switched Voyager 2 over to a set of backup thrusters that hadn't fired in 37 years, and those thrusters worked flawlessly. Picture debugging software written half a century ago, running on hardware you'll never physically touch, where a single command takes more than 22 hours just to arrive. Power comes from radioisotope thermoelectric generators, 3 per spacecraft, each containing plutonium-238 that decays naturally and releases heat, which thermocouples then convert into electricity. At launch, each spacecraft produced about 470 watts, but plutonium doesn't decay forever at full strength. The output steadily drops, losing roughly 4 watts every year. By 2026, Voyager 1 is left with only about 249 watts. This slow fade is the defining constraint on the whole mission. Every instrument, every heater, every transmitter pulls from this shrinking pool of power, and as it dwindles, engineers must keep choosing what to switch off. The cameras were shut down back in 1990. Various other instruments have gone dark in the years since. By the late 2020s, there simply won't be enough power left to run anything at all, and the spacecraft will finally fall quiet. Communication happens through the Deep Space Network, 3 enormous radio antenna complexes spread across California, Spain, and Australia, positioned so that at least one is always facing the spacecraft as Earth rotates. Each dish measures 230 feet across. A signal from Voyager 1 needs more than 22 hours to reach us, from Voyager 2 about 18 hours. When engineers send an instruction, they wait through those long hours for it to arrive, then wait again for confirmation it was received, a simple round trip that for Voyager 1 takes over 44 hours in total. Each spacecraft transmits with only about 23 watts of power, less than a typical light bulb. By the time that whisper of a signal crosses billions of miles and reaches Earth, it has faded to roughly 1/quintillionth of a watt. Among the faintest signals humans routinely manage to detect and decode. This, remember, is the very technology that uncovered what waits at the solar system's edge. Computers holding less memory than a microwave oven. Transmitters weaker than a refrigerator light. Instruments designed with slide rules rather than supercomputers. Keep that picture in mind as we walk through what they found, because what comes next quietly astonished every scientist who studied the incoming data. Voyager 1 reached the termination shock on December 16, 2004, at a distance of 94 AU from the Sun, about 8.7 billion miles out. Scientists had expected that shock somewhere between 75 and 90 AU. Voyager was already past that entire range before it arrived. The termination shock, recall, marks where the solar wind abruptly drops from supersonic to subsonic speed, a genuine physical boundary where plasma compresses and heats. And Voyager found it sitting noticeably farther out than anyone had calculated. But here's where things got strange. The crossing wasn't a single clean event. Voyager first detected shock-like signatures on August 1, 2002 at 85 AU. Then, oddly, the shock seemed to move. Over the following months, the boundary drifted farther outward, and Voyager found itself back in ordinary, still, supersonic solar wind. The telltale signs of the shock disappeared entirely. In 2003, the signatures reappeared. The shock washed back over the spacecraft as it pressed onward, then retreated again. It wasn't until December 16, 2004, that Voyager finally crossed for good, settling into the slower, denser plasma beyond. This restless, breathing quality of the boundary traces back to solar activity itself. When the Sun produces strong outbursts, the added pressure in the solar wind pushes the shock farther from the Sun. When solar activity quiets down, the shock retreats inward again. The boundary, it turns out, isn't fixed in place at all. It's alive, constantly shifting. Voyager 2 crossed its own termination shock on August 30, 2007 at 84 AU, roughly 7.8 billion miles from the Sun. And here's the puzzle. Voyager 2 crossed closer to the Sun than Voyager 1 had by about 10 AU, or some 930 million miles. If this boundary were a perfect sphere, both spacecraft should have crossed at nearly identical distances. Instead, here was the first solid proof that the shape wasn't what anyone expected. The heliosphere isn't a simple, even bubble. It's squeezed in some directions and stretched out in others. Voyager 1 was heading roughly toward the nose. The the direction the sun moves through the galaxy, while Voyager 2 was angled more toward the side. The nose gets compressed by the sun's own motion, much like the bow wave that forms ahead of a moving boat, while the sides and the trailing tail stretch out behind. The two spacecraft, without meaning to, were sampling two very different regions of one lopsided structure. Scientists had suspected something like this might be true. Now they finally had the evidence in hand. After crossing the termination shock, both spacecraft entered a region called the heliosheath. A zone that was supposed to be relatively predictable, slowed solar wind plasma pushing outward and sideways, turbulent but broadly understood. A transition layer between the shocked solar wind and true interstellar space. Scientists expected Voyager to spend somewhere between 5 and 10 years crossing this region before reaching the heliopause, with the heliosheath itself stretching maybe 10 to 20 AU thick. Based on Voyager 1's position and speed, the crossing was projected to happen around 2015, somewhere near 100 to 110 AU. But starting in 2010, something unanticipated began showing up in the data. Voyager 1 started registering climbing levels of galactic cosmic rays, those high-energy particles born in supernovae and other violent events across the galaxy. Models expected their intensity to jump sharply right at the heliopause, not gradually rise while the spacecraft was still deep in the heliosheath. At the same time, lower energy particles coming from the sun itself were slowly fading, when they were expected to vanish abruptly at the heliopause, not taper off gradually beforehand. And Voyager was still clearly inside the heliosheath. Solar wind plasma was still there. The magnetic field still carried the signature of the sun's own field. So what exactly was happening? Then, in June 2012, Voyager 1 detected something entirely new. A region where the magnetic field lines ran perfectly straight outward from the sun, radially aligned, no twisting, no tangling, just clean and orderly, with particles flowing along these lines in both directions at once. Solar particles streaming outward, galactic cosmic rays streaming inward. The field lines behaved like a highway connecting the heliosheath directly to interstellar space. Scientists began calling it the magnetic highway. No model had ever predicted such a thing. Nobody had imagined a structure like this could even exist. The leading explanation is that the sun's magnetic field was, in this spot, merging directly with the galaxy's own field, letting particles travel freely in both directions, like a bridge spanning two regions that should otherwise stay separate. Voyager 1 spent roughly 2 months inside this magnetic highway. During that stretch, cosmic ray intensity climbed higher than anywhere else measured in the heliosheath, while solar particle intensity dropped lower. The spacecraft, in effect, was sampling a region with a direct line to interstellar space, even though it hadn't technically crossed the heliopause yet. Then, on August 25, 2012, everything shifted at once. Solar wind particles all but disappeared. Cosmic rays jumped to a high, steady plateau. The change played out over just a few days. And yet the magnetic field's direction didn't rotate at all. It kept pointing the same way it had throughout the entire heliosheath. This left scientists genuinely puzzled. Some argued Voyager had clearly crossed the heliopause, since the vanishing solar particles and surging cosmic rays pointed that way. Others countered that the absence of any magnetic rotation meant it hadn't, that perhaps this was some in-between region, or that the heliopause itself had multiple layers. The debate stretched on for more than a year. Finally, in September 2013, NASA officially announced that Voyager 1 had crossed the heliopause back in 2012. The spacecraft was, at that point, sitting at 121 AU, some 11.2 billion miles from the Sun, far beyond anything the models had forecast. Not 90 to 100 AU, but 121, some 20 to 30% farther out than predicted, 2.4 billion miles beyond where scientists had drawn the line. This is quietly astonishing discovery number one. The heliopause simply isn't where the models placed it, and this isn't a small rounding error. It's an error measured in billions of miles. It suggests either the solar wind pushes harder than assumed, or the interstellar medium pushes back with less force than estimated, or perhaps some combination of both. Later analysis points toward the local interstellar medium being somewhat less dense than expected, not drastically so, but enough to shift that balance point outward by 20 to 30%. This matters because the heliosphere functions as a kind of shield against galactic cosmic rays, and a larger heliosphere means better shielding. Something that could shape cosmic ray exposure on Earth across geological timescales, potentially touching climate, atmospheric chemistry, even mutation rates over deep time. But distance wasn't the only surprise waiting. Scientists had expected the heliosphere to be roughly spherical, perhaps stretched somewhat opposite the Sun's direction of travel like a comet's tail, but basically symmetric overall. What they actually found looked quite different, a shape closer to a bullet or a teardrop. The leading edge, where the Sun pushes through the interstellar medium, is squeezed into a blunt, compressed nose. The sides flatten out, and the tail stretches away behind for what could be hundreds of astronomical units. Voyager 1 crossed at 121 AU, heading roughly toward that nose. Voyager 2 crossed on November 5, 2018 at 119 AU, but was traveling in a different direction, more toward the flank. Curiously, both crossed at nearly the same distance from the Sun, which tells us the heliosphere isn't dramatically stretched out at its equator. The asymmetry here is subtler than that. The compression at the nose comes directly from the Sun's own motion through the galaxy, roughly 137 kilometers per second, or about 490,000 miles per hour. From the Sun's perspective, the interstellar medium arrives as a headwind striking the heliosphere from the front, squeezing that leading edge inward. Beyond the heliopause, models predict there should be a bow shock forming in the interstellar medium itself, not unlike the wave that builds ahead of a moving boat somewhere between 140 and 230 AU. But given how far off the models were about the heliopause itself, that bow shock could genuinely be almost anywhere. Neither spacecraft has reached it yet. This shape matters for more than aesthetics. It affects how easily cosmic rays can reach the inner solar system. A perfectly spherical heliosphere would let cosmic rays in equally from every direction. But a bullet-shaped one lets them slip in more easily from some angles than others. The long tail, in particular, might offer an easier path for cosmic rays sneaking in from behind. The shape also shapes how the solar system interacts with the wider interstellar landscape. Our Sun currently sits inside something called the local interstellar cloud, a slightly denser patch of gas stretching a few light-years across. The edges of this cloud help determine how compressed the heliosphere becomes. in a matter of thousands of years. The sun will drift out of this cloud entirely and into a different region, where the surrounding pressure will change and the heliosphere's shape and size will shift along with it. What the Voyagers are giving us, really, is a single snapshot of this boundary as it happens to exist right now. A future mission might well measure something quite different. This is quietly astonishing discovery number 2. The shape itself is wrong, asymmetric and dynamic, shaped by the sun's motion through the galaxy rather than the tidy bubble scientists had drawn on paper. Scientists had also expected the passage from the heliosheath into true interstellar space to be a fairly tidy affair, a boundary where, across a few weeks or months, solar plasma would fade away, cosmic rays would climb, and the magnetic field would swing around to its new orientation. A clean handoff. Instead, Voyager 1's approach to the heliopause stretched across more than 2 years. Starting in 2010, cosmic rays crept steadily upward while the spacecraft was still clearly registering solar plasma. By 2012, it had entered that unexpected magnetic highway, where particles streamed along field lines linking the heliosheath directly to interstellar space. Then, on August 25, 2012, solar particles vanished and cosmic rays surged, and yet the magnetic field refused to rotate. Months of debate followed before scientists finally realized the local galactic field simply happened to run roughly parallel to the sun's own field in that particular patch of sky. A pure coincidence. Crossing the boundary didn't produce a dramatic swing in field direction because both sides, as it happened, were already pointing the same way. Voyager 2's crossing told a different story entirely. It unfolded over roughly a single day on November 5, 2018, far quicker than its twin's drawn-out passage. And this time, the magnetic field did rotate by about 20 degrees, not a dramatic flip, but a clear, measurable shift. Why the difference between the two? Simply put, the spacecraft crossed in different locations, and the boundary itself isn't uniform. Near Voyager 1's path, close to the nose, the heliosphere is compressed, and the boundary there may be thicker or more layered, with that magnetic highway phenomenon more likely to appear. Near Voyager 2's path, closer to the side, the transition is sharper and quicker, with different magnetic geometry altogether. Both spacecraft also picked up on oscillations even after crossing. Voyager 1 briefly detected solar particles again in August 2013, nearly a full year after its official crossing, before they faded once more. The boundary, it seems, washed back over the spacecraft and then withdrew. These oscillations trace back to solar activity. Strong bursts of solar wind travel outward through the heliosphere, and when they slam into the heliopause, they temporarily shove the boundary farther out, letting it pass over a spacecraft's position before contracting again once the pulse dies down. A storm erupting on the Sun in 2012 might not reach the boundary until 2014 or 2015. Voyager, in effect, caught the heliopause in the act of breathing, expanding and contracting in response to solar weather happening billions of miles away. Nobody had predicted this kind of behavior. The models treated the heliopause as something that shifted slowly over the years, tracking the broader solar cycle. Not something oscillating rapidly enough over mere weeks or months to cross back and forth over a spacecraft that wasn't even moving relative to it. What this tells us is that the edge of the solar system isn't fixed. It's not a line you can point to and say definitively, this is where it ends. The boundary genuinely moves, sometimes by several astronomical units over surprisingly short stretches of time. If you found yourself sitting at 120 AU, are you inside the solar system or out in interstellar space? The honest answer depends entirely on when you happen to ask. Right now, you might be in interstellar space. A month later, once a solar pulse arrives, you might find yourself briefly back inside the heliosheath. A few months after that, you're back in interstellar territory again. This is quietly astonishing discovery number 3. The transition itself is layered, prolonged and dynamic, full of multiple crossings, an unexpected magnetic highway, and slow oscillations, nothing at all like the clean single boundary scientists had drawn up in advance. Voyager 1 holds the distinction of being the first spacecraft to directly sample interstellar material. Before its crossing, everything we knew about interstellar space came second-hand, through spectroscopy of distant stars, radio observations of hydrogen clouds, and theoretical modeling. Voyager, by contrast, actually reached out and measured it, dipping instruments straight into the medium and taking readings. The density there measures about 0.08 particles per cubic centimeter. Our best laboratory vacuum chambers on Earth manage densities around 1 million particles per cubic centimeter, meaning interstellar space is a cleaner vacuum than anything we've engineered. And yet it still isn't empty. That works out to roughly 80,000 particles per cubic meter, compared to about 10 to the 25th particles in the same volume of air at sea level, making interstellar space something like 10 trillion times less dense than the air we breathe. Still present, just barely. The temperature reads somewhere between 54,000 and 90,000 degrees Fahrenheit. Which sounds scorching, but temperature really just measures the average kinetic energy of particles, not how much heat they can actually deliver. With so few particles around, even a blistering temperature carries very little heat energy. An astronaut drifting through interstellar space would freeze rather than burn. There simply aren't enough particles present to transfer warmth. The pressure comes in at roughly 0.00000003 pascals, compared to Earth's sea level pressure of about 101,000 pascals. Meaning interstellar pressure sits at something like 110 trillionths of what we feel here. And yet, faint as it is, this pressure is exactly what balances the outward push of the solar wind at the heliopause. Voyager also picked up plasma oscillations out there, waves of compression and rarefaction rippling through the medium. In 2012 and 2013, Voyager 1 registered several bursts of these oscillations, and their frequency let scientists calculate the local electron density. Different bursts gave slightly different readings, revealing that the density isn't perfectly uniform. It varies by something like 10 to 20% across distances of just a few astronomical units. These variations shape how the heliopause itself is structured, since denser patches press harder against the heliosphere from their direction, while thinner patches let it expand more freely. The interstellar medium also carries its own magnetic field, part of the galaxy's larger structure. Voyager 2 measured that field at roughly 50 nanotesla, compared to Earth's surface field of about 50,000 nanotesla, meaning the interstellar field is only about a millionth as strong as our own planet's. But across truly vast distances, even a field this faint still matters. shaping how plasma flows, accelerating cosmic rays, and quietly linking star systems across the galaxy into one enormous web of field lines. None of these measurements lined up exactly with what models had predicted. Density came in a bit higher or lower than expected. Temperature differed slightly. Magnetic field strength and orientation weren't quite what the models called for. Each new reading has forced scientists to refine their thinking and revise their models a little further. This is quietly astonishing discovery number 4. The properties of interstellar space simply don't match the models. The first direct measurements reveal real differences in density, temperature, pressure, and magnetic field, small differences individually, but ones that genuinely matter. Among Voyager 1's most surprising finds is something scientists now call tsunami waves, shock waves rippling through the interstellar medium that actually originate from our own sun. Whenever the sun unleashes a powerful outburst, a coronal mass ejection, or an intense solar wind burst, that pulse travels outward through the heliosphere. When it eventually reaches the heliopause, it strikes like a hammer blow, launching a shock wave onward into the interstellar medium itself. These waves travel at the local speed of sound in that plasma, roughly 60 kilometers per second, far slower than the solar wind itself, but still fast enough to cross several astronomical units within a year. Voyager 1 caught its first tsunami wave in October and November of 2012, when its plasma wave instrument picked up oscillations lasting several weeks, their specific frequency allowing scientists to calculate the local electron density. A second wave arrived in April and May of 2013 at a slightly different frequency, hinting that the density had shifted somewhat. A third wave followed in March 2014 and a fourth in 2015. Each wave traces back to a solar outburst that happened years earlier. The sun flares, the pulse races outward at supersonic speed through the heliosphere, strikes the heliopause, and sends a shock wave rippling into interstellar space. Months or years later, Voyager, sitting far beyond the heliopause, feels that same wave pass over it. This tells us something remarkable. The sun's influence stretches far beyond the heliopause itself, not as solar wind plasma, which stays confined within the heliosphere, but as pressure waves, genuine shock waves traveling through the wider interstellar medium. These waves probably don't travel forever. They likely dissipate gradually as their energy spreads across an ever larger area. But they clearly travel significant distances, possibly tens of astronomical units beyond the heliopause. Their detection also served as independent confirmation that Voyager really had crossed into interstellar space, since these waves arrived from the sun's direction after traveling through interstellar plasma. Had Voyager still been inside the heliosheath, it would have registered the original solar wind pulses directly, not shock waves propagating through the interstellar medium. Nobody had anticipated any of this. Scientists knew shock waves existed out in the interstellar medium generated by supernovae, but nobody expected the sun's own outbursts to remain detectable billions of miles past the heliopause. This is quietly astonishing discovery number 5. Tsunami waves from solar storms genuinely propagate through interstellar space, meaning the sun's reach extends much farther than anyone had imagined. Perhaps the most puzzling discovery of all concerns the orientation of the magnetic field in interstellar space. Before Voyager 1 crossed over, Models predicted the galactic field would point in a distinctly different direction from the Sun's own field. The Sun's field runs generally outward in a radial pattern, though twisted by rotation and turbulence, while the galactic field was expected to follow the broader structure of the Milky Way. Our own region sits within the Orion Arm, a minor spiral arm, and the galactic field there was expected to run roughly parallel to that arm. So crossing the heliopause, in theory, should have shown some clear rotation in the magnetic field, not necessarily dramatic, but a noticeable shift marking the handover from Sun-dominated to galaxy-dominated territory. Voyager 1 detected nothing of the sort. The field's direction after crossing looked essentially identical to what it had been before, sparking months of confusion and debate. Eventually, scientists concluded that the local galactic field simply happens to run roughly parallel to the Sun's own field in this particular pocket of space. Sheer coincidence. The field lines out there just happen to point in almost the same direction as the heliosphere's field did at Voyager 1's crossing point. Voyager 2's crossing, on the other hand, showed a modest rotation of about 20 degrees. Not dramatic, but clearly measurable. This tells us the field's direction in nearby interstellar space isn't uniform at all. It varies. At Voyager 1's location, it points one way. At Voyager 2's location, more than 100 AU away in a different direction, it points slightly differently. That actually makes sense, since the interstellar field isn't a simple uniform structure like a bar magnet. It's tangled and twisted by plasma currents and the influence of nearby stars. But it also means we can't easily extend our understanding from just 2 data points. We have measurements from 2 locations separated by over 100 astronomical units, and they differ. How does the field vary in between? How does it vary in other directions entirely? We simply don't know yet. This matters because the magnetic field shapes how cosmic rays travel. Charged particles spiral along field lines as they move, and those lines act like channels, guiding particles one way or another. Favorably oriented galactic field lines can funnel cosmic rays into the heliosphere, while unfavorably oriented ones deflect them away. Understanding the local structure of the galactic field is essential for understanding cosmic ray exposure here on Earth. Since these rays influence atmospheric chemistry, produce isotopes like carbon-14 used in dating, may play a role in cloud formation, and contribute to radiation exposure for astronauts. Over geological timescales, cosmic ray flux has clearly varied, something we can see in isotope records preserved in ice cores and sediments. Some of that variation traces back to shifts in Earth's own magnetic field, some to nearby supernova explosions, and some possibly to changes in heliosphere shielding as the Sun drifts through regions of differing interstellar pressure. What the Voyagers have given us is a snapshot of the current configuration, but that configuration isn't fixed. It shifts as the Sun continues its slow journey through the galaxy. This is quietly astonishing discovery number 6. The magnetic field's orientation caught everyone off guard, and it varies noticeably even between 2 points barely 100 astronomical units apart. Galactic cosmic rays are high-energy particles, mostly protons, arriving from beyond our solar system. Accelerated by supernova shockwaves, pulsar winds, and other violent cosmic events. They carry energies ranging from millions to trillions of electron volts, with some exceeding even what the Large Hadron Collider can produce. The Voyagers measured both the intensity and composition of these particles, aiming to understand precisely how the heliosphere shields us from them. As Voyager 1 pushed through the heliosheath, cosmic ray intensity climbed gradually. Exactly as expected, the deeper into the heliosheath, the weaker the shielding and the more cosmic rays could slip through. But the direction these rays were arriving from turned out to be surprising. Scientists had anticipated roughly even intensity from every direction. Instead, there was clear asymmetry, more arriving from certain directions than others. Once Voyager 1 crossed the heliopause, cosmic ray intensity jumped to a new plateau, roughly 10 to 20% higher than what it had measured within the heliosheath, confirming that the heliosphere really does provide meaningful shielding. Reducing cosmic ray intensity even out in its farthest reaches, billions of miles from the Sun, by that same 10 to 20% compared to true interstellar space. And again, the directional pattern defied expectation. The rays weren't arriving uniformly, showing clear enhancement from certain directions and a deficit from others. Voyager 2 confirmed the same pattern after its own crossing. Higher cosmic ray intensity out in interstellar space than within the heliosheath, and the same directional unevenness. This asymmetry hints that the local interstellar medium has real structure, perhaps nearby sources like old supernova remnants, or a galactic magnetic field that channels cosmic rays preferentially from certain directions. Curiously, both spacecraft detected lower cosmic ray intensity coming from the direction of the galactic center, which seems backward at first. Since the galactic center holds the highest concentration of stars and the most supernova activity, and you'd expect more cosmic rays streaming from that direction, not fewer. The likely explanation is that the galactic magnetic field grows stronger toward the center, trapping and scattering cosmic rays as they try to propagate outward from the inner galaxy, so fewer of them ever reach our local neighborhood from that direction. This remains an active area of research. The Voyagers gave us our first direct measurements of cosmic ray intensity and directionality out in interstellar space, but two measurements from two locations can't fully map a three-dimensional structure. Future missions will need to explore other directions entirely. This is quietly astonishing discovery number 7. Cosmic rays arrive preferentially from unexpected directions, and their source distribution doesn't match the simple models scientists once relied on. So how exactly did we arrive at this point? How did two spacecraft, designed for a modest 5-year mission, end up making these discoveries some 11 billion miles from home? The story really begins at Jupiter. Voyager 1 arrived there in March 1979, with Voyager 2 following in July of that same year. These encounters completely reshaped our understanding of the solar system's largest planet. Jupiter's atmosphere revealed far more intricacy than anyone anticipated. The Great Red Spot, in particular, showed remarkable internal structure. Before Voyager, astronomers knew the spot existed, but had no real sense of what caused it or how deep it ran. Voyager's images revealed it as a high-pressure system. An anticyclone spinning counterclockwise, its storm clouds rising roughly 5 miles above the surrounding cloud deck. Its distinctive color comes from complex organic molecules formed when sunlight breaks down simpler compounds in the atmosphere. Elsewhere, Dozens of smaller storms dot the clouds, white ovals and brown barges, each one larger than most hurricanes here on Earth, occasionally merging or slipping past one another in an intricate dance governed by Jupiter's powerful winds and rapid spin. Lightning flickers through the atmosphere too, similar in nature to Earth's own lightning, an electrical discharge between clouds or between clouds and deeper atmospheric layers. Though Jupiter's bolts are immense, some releasing 1,000 times more energy than a typical bolt on Earth. Auroras blaze at both poles, echoing Earth's own northern and southern lights, but far more powerful. Where Earth's auroras form when solar wind particles collide with atmospheric molecules, Jupiter's are driven by its own rotation and magnetic field. As that field sweeps through space, it gathers up charged particles thrown off by volcanic activity on the moon Io, and those particles spiral along field lines toward the poles, slamming into Jupiter's upper atmosphere at tremendous speed. The resulting auroras shine roughly 1,000 times brighter than Earth's, stretching across thousands of miles of polar sky. Cloud bands race along at winds exceeding 400 miles per hour, dwarfing Earth's jet streams, which top out around 200. This ferocious wind speed comes down to Jupiter's rapid spin. The planet completes a full rotation in under 10 hours despite being 11 times wider than Earth. And that spin generates powerful Coriolis forces that organize the atmosphere into alternating bands of eastward and westward flowing wind. But the real surprises came from Jupiter's moons. Astronomers had known about its 4 large satellites since Galileo first spotted them in 1610, Io, Europa, Ganymede and Callisto, collectively the Galilean moons. From Earth, they had always appeared as nothing more than faint points of light. No telescope could resolve any surface detail, leaving astronomers able to measure only their size, orbit, and brightness. Voyager changed all of that. Io, the innermost of the 4, was expected to be a cold, geologically dead world, much like Earth's own moon. Linda Morabito, a navigation engineer, was reviewing images to pin down Voyager 1's precise position when she noticed something strange, an umbrella-shaped plume rising from Io's edge. It turned out to be a volcanic eruption, the first active volcano ever discovered anywhere beyond Earth. Io, as it turns out, is the most volcanically active body in the entire solar system. Voyager caught 9 active volcanoes during its flybys alone, and later observations have catalogued more than 400 volcanic centers across its surface. That surface is constantly being repaved by sulfur and silicate lava, giving Io its striking yellow, orange, and red coloring. Some plumes reach heights of nearly 200 miles, hurling material outward at speeds topping 1,000 miles per hour. All that volcanic energy comes from tidal heating. Jupiter's enormous gravity, combined with the gravitational tug of Europa and Ganymede, constantly flexes Io's interior, and that flexing generates friction, which generates heat, which melts rock and erupts as lava. A process long theorized but never confirmed until Voyager proved it. This discovery reshaped how scientists think about what powers geological activity on other worlds. It isn't only radioactive decay inside a planet's core that can drive it. Tidal heating from gravitational interactions can power volcanism and tectonics too. A mechanism that applies to Io, to Europa, to Saturn's moon Enceladus, and potentially to exomoons orbiting giant planets around other stars entirely. Europa presented a very different kind of puzzle. Its surface is smooth ice, crisscrossed with cracks and ridges, and remarkably few craters, hinting at a young surface that's been continually renewed. The ice appears fractured and refrozen in intricate patterns, long, straight cracks called lineae stretch for hundreds of miles, while some regions show chaotic terrain where the ice seems to have broken apart and reformed. The implication here runs deep. Beneath that icy shell might lie liquid water, an ocean kept from freezing by tidal heating, weaker than Io's, but perhaps enough. The same gravitational tug of war tearing Io apart might be gently warming Europa's interior, just enough to keep water liquid under the ice. Voyager couldn't confirm the ocean directly. The evidence was circumstantial, drawn from surface features and modelling. But the mere possibility that an icy moon might be hiding an ocean made Europa one of the most compelling places to search for life beyond Earth. Later missions, particularly Galileo in the 1990s and 2000s, would strengthen that case considerably, detecting magnetic signatures suggesting a conducting layer beneath the surface, and surface chemistry hinting at salts that might have leached up from an ocean below. But it was Voyager that offered the very first hint, the first suggestion that an icy moon might be quietly hiding a sea. Ganymede, the solar system's largest moon, revealed its own complex surface. Ancient, dark, heavily cratered terrain sitting alongside younger, brighter regions marked by grooves and ridges, suggesting the moon underwent some kind of geological resurfacing at some point in its past. Callisto, the outermost of the Galilean moons, appeared heavily cratered throughout, its surface seemingly ancient and largely unchanged for billions of years. A striking contrast to Io's constantly refreshed landscape. Voyager also discovered that Jupiter has rings of its own faint, made of dust-sized particles, nothing like the spectacular ice rings circling Saturn. Astronomers had suspected rings might exist around Jupiter, but had never actually detected them from Earth. Voyager 1 confirmed their presence in 1979, thin and faint, but undeniably there, a discovery suggesting ring systems might be far more common around giant planets than anyone had assumed, some as dramatic as Saturn's, others as faint as Jupiter's own. By the time both spacecraft moved on from Jupiter, they had returned more data than every previous observation of the planet combined. Thousands of images, detailed measurements of magnetic fields, radiation environments, and atmospheric chemistry, close study of 4 major moons and several smaller ones, and the discovery of an entirely new ring system. The mission had already proven itself a spectacular success. And Saturn was next. Voyager 1 reached Saturn in November 1980, with Voyager 2 arriving in August 1981. Saturn's rings had been observed since Galileo first glimpsed them in 1610, though he didn't fully grasp what he was seeing at the time, describing them almost as handles or ears attached to the planet. It wasn't until the 1650s that Christian Huygens correctly identified them as a ring encircling Saturn. By the 1980s, astronomers already knew Saturn possessed multiple rings separated by gaps: the A ring, the B ring, the C ring, and the wide gap between the A and B rings known as the Cassini division. But nobody had any idea just how intricate the true structure really was. Voyager revealed that each of these broad, visible rings is actually made up of thousands of individual ringlets, structure far too fine to resolve from Earth. The rings aren't solid sheets at all. They're made of billions of individual particles ranging from dust grains up to boulders the size of a house, each one following its own orbit according to the ordinary laws of celestial mechanics. The rings displayed waves, braids, kinks and spokes, dark radial markings that rotate along with the rings themselves. The mechanism behind those spokes wasn't immediately clear. Later analysis suggested they're caused by dust particles being electrostatically lifted above the ring plane. Tiny shepherd moons, orbiting near the edges of certain rings, use their gravity to herd nearby ring particles and keep boundaries crisp. Prometheus and Pandora, a pair of small moons flanking the F ring, keep that ring corralled through their combined gravitational pull. That F ring, in particular, showed a braided structure unlike anything seen anywhere else, several strands appearing to wind around one another, and later observations revealed those braids shift over time as the shepherd moons continue to nudge the ring particles around. The sheer complexity on display was startling. Saturn's rings aren't simply bands of debris. They form a dynamic system where gravity, orbital mechanics, and particle collisions generate structure at every scale, from features spanning thousands of miles down to individual particles just a few feet across. Density waves ripple through the rings much like sound waves, but driven by gravitational resonances with Saturn's moons. Wherever particles orbit at particular ratios relative to a moon's own orbit, repeated gravitational tugs build up into waves that compress and stretch the ring material into spiral patterns. Bending waves appear too, warping the ring plane vertically in response to these same gravitational nudges. And despite spanning thousands of miles across, the rings themselves are remarkably thin, only about 30 feet thick in most places, proportionally thinner than a sheet of paper laid across a beach ball the size of Saturn. Titan, Saturn's largest moon, was already known to carry an atmosphere, the only moon in the solar system with one thick enough to rival an actual planet's. This had been understood since the 1940s, when Gerard Cooper detected methane absorption lines in Titan's spectrum. Voyager 1 made a close pass, flying within 2,500 miles of the moon's surface, a trajectory that came at a real cost. Reaching Titan this closely meant Voyager 1 could no longer continue on to Uranus and Neptune, which is precisely why Voyager 2 took over that leg of the journey. But the encounter with Titan more than justified the trade-off. Titan's atmosphere turned out to be even thicker than expected, with surface pressure roughly 1.5 times that of Earth at sea level, higher than any other moon or planet aside from Venus. Its composition is mostly nitrogen, much like our own atmosphere, around 95%, with the remainder made up of methane and other organic compounds, methane, ethane, propane, acetylene, evidence of genuinely complex organic chemistry playing out overhead. The surface itself stays hidden beneath a thick, opaque orange haze, layers of photochemical smog produced when sunlight breaks methane apart. That smog is made of tholins, complex organic molecules resembling compounds that may once have existed on early Earth. Voyager's cameras couldn't see past that haze to the surface below, but the atmospheric data alone proved fascinating, detailed readings of temperature, pressure, and composition at different altitudes. Titan, it turns out, has its own methane cycle, echoing Earth's water cycle, Methane evaporates from the surface, forms clouds, and rains back down again. The surface likely holds lakes or seas of liquid methane and ethane, along with rivers and streams carrying liquid hydrocarbons across the landscape, all shaped by organic chemistry driven by sunlight breaking down methane into more complex molecules. Surface temperature hovers around minus 290 degrees Fahrenheit, cold enough to turn water ice as hard as rock, yet warm enough for methane to exist as a flowing liquid. After Saturn, the two spacecraft parted ways. Voyager 1 was sent on a path tilted above the plane of the solar system, heading toward interstellar space as directly as possible, with no more planetary visits ahead of it. Voyager 2 pressed onward toward Uranus and Neptune, and to this day remains the only spacecraft ever to have visited either of these distant ice giants. Voyager 2 reached Uranus in January 1986. Uranus is famously strange, tilted 98 degrees relative to its orbital plane, so that it essentially rolls along its orbit like a barrel rather than spinning upright like a top. This means its poles alternate between facing toward and away from the Sun across its 84-year orbit, each one enduring 42 years of unbroken daylight, followed by 42 years of darkness. Voyager 2 found Uranus's atmosphere surprisingly bland, with few visible cloud features and a pale blue color caused by methane absorbing red light, alongside winds reaching 560 miles per hour. It also turned up 10 previously unknown moons and 2 new rings, adding to the 9 already known. But the most compelling discoveries came from the small moon Miranda, which showed bizarre patchwork geology, regions of ancient, heavily cratered terrain sitting right beside areas of grooved terrain marked by parallel ridges and valleys. Enormous cliffs mark its surface too, including Verona Rupes, estimated at roughly 6 miles high, more than triple the height of the canyon walls in Mars's Valles Marineris. The whole surface looks as though it had been shattered and pieced back together. One theory suggests Miranda really was broken apart by a massive impact and later reassembled from the scattered debris, mixing different terrain types together in the process. Another theory points to tidal heating, though Miranda's current orbit doesn't generate nearly enough stress to explain it, suggesting its orbit may have looked quite different in the past. The true cause remains uncertain, but Miranda clearly went through something dramatic. Voyager 2 arrived at Neptune in August 1989, the farthest planet from the Sun, nearly 3 billion miles from Earth. This flyby marked the true culmination of the Grand Tour 12 years after launch, having successfully visited all 4 outer giants. Scientists had expected Neptune to resemble Uranus, another relatively bland ice giant with little going on atmospherically. Instead, Neptune turned out to have the most dynamic atmosphere of any planet the mission visited. It showed off the Great Dark Spot, an Earth-sized storm reminiscent of Jupiter's Great Red Spot, along with a bright cloud feature nicknamed the Scooter that circled the planet roughly every 16 hours, and winds clocking in above 1,900 miles per hour, the fastest winds ever measured on any planet in our solar system. Neptune's largest moon, Triton, delivered its own surprise. Triton orbits Neptune backward in a retrograde direction opposite the planet's own rotation, extraordinarily unusual for a moon of its size. The implication is that Triton didn't form alongside Neptune at all. It was almost certainly captured, likely originating in the Kuiper belt. Triton also showed active geology, with nitrogen ice geysers erupting straight from its surface, remarkable given that surface temperatures there sit around minus 391 degrees Fahrenheit, among the coldest surfaces ever measured in the solar system, and yet still geologically alive. The likely mechanism is seasonal heating. Even at Triton's extreme distance, sunlight can still warm darker patches beneath a layer of translucent nitrogen ice, causing the nitrogen to sublime directly from solid to gas and build up pressure until it eventually ruptures the surface, venting gas into space and carrying dark particles that fall back down as streaks across the ice. With Neptune behind it, Voyager 2's planetary mission came to a close. Between them, the two spacecraft had uncovered active volcanism on Io, hints of a hidden ocean beneath Europa's ice, Jupiter's faint ring system, thousands of individual ringlets within Saturn's rings, Titan's remarkably thick atmosphere, Miranda's strange patchwork geology, Neptune's turbulent atmosphere and record-breaking winds, and Triton's icy geysers, along with tens of thousands of images and measurements that reshaped our understanding of the outer solar system entirely. And remarkably, both spacecraft were still functioning, still transmitting data, still capable of real science. So NASA made a call. The Voyager interstellar mission would begin. The spacecraft would keep traveling outward, searching for the boundary where the sun's influence finally gives way. No spacecraft had ever ventured that far before. Scientists had their models, their predictions, all of which, as we've seen, would turn out to be wrong. The planetary successes had, if anything, made scientists more confident in their forecasts for the edge. After all, the models had worked well for the planets, so surely they'd hold for the heliopause too. But the edge of the solar system isn't a planet. It's a dynamic boundary between two plasmas, and it proved to be far stranger than anyone had dared imagine. These discoveries carry real weight for anyone thinking seriously about interstellar travel, since they've given us our first direct measurements of the environment any interstellar spacecraft would actually have to cross. And honestly, the picture that emerges is a sobering one. Voyager 1 has now been traveling for nearly 50 years, covering roughly 159 astronomical units, about 14.8 billion miles. That sounds impressive, until you consider how far it still is to even the nearest star. Proxima Centauri, our closest stellar neighbor, sits 4.24 light-years away. Something like 268,000 astronomical units, roughly 25 trillion miles. At Voyager's current pace, reaching Proxima Centauri would take about 73,000 years, longer than the whole of recorded human history, longer than we've practiced agriculture, longer than the time since the last ice age ended. And Voyager isn't even heading toward Proxima Centauri, it's traveling in an entirely different direction. The star it will eventually pass nearest to is Gliese 445 in roughly 40,000 years, though nearest here still means 1.6 light-years away, about 9.4 trillion miles. Voyager won't enter that star's system at all. It will simply drift past through the vast emptiness separating the stars. Voyager 2, for its part, will pass within 1.7 light-years of Ross 248 on a similar timescale. Again, nowhere near close enough to count as a true encounter. These staggering timescales reveal the core challenge facing interstellar travel. The distances involved are so immense that even speeds of tens of thousands of miles per hour turn out to be hopelessly slow. To make interstellar journeys genuinely feasible, you'd need velocities dramatically higher, at least a few percent of light speed, and perhaps closer to 10% for anything resembling a reasonable travel time to nearby stars. 10% of light speed comes out to roughly 67 million miles per hour, about 7,300 times faster than Voyager's current pace. At that velocity, Proxima Centauri would be about 42 years away. Still a lifetime, admittedly, but well within the span of a human career. You could realistically launch such a mission and still be alive when the first data started arriving home. But reaching even 10% of light speed demands an enormous amount of energy, and Voyager's discoveries reveal additional hurdles along the way. The interstellar medium, however faint, isn't truly empty. It holds about 0.08 atoms per cubic centimeter, mostly hydrogen and helium. At Voyager's leisurely pace, this barely registers. The spacecraft occasionally collides with a stray hydrogen atom, and the effect is negligible. But at 10% of light speed, every single collision becomes meaningful, since kinetic energy scales with the square of velocity. A collision at that speed carries roughly 28 million times more energy than an equivalent collision at Voyager's current pace. A single hydrogen atom striking a spacecraft moving at 10% of light speed delivers about 6 electron volts of energy, which sounds trivial, except there are an enormous number of these atoms out there. A spacecraft with just 1 square meter of cross-section traveling at that velocity would be struck by roughly 10 to the 14th hydrogen atoms every second, on the order of 100 trillion impacts per second. Each individual collision delivers only a tiny amount of energy, but collectively they add up to several thousand watts of continuous power deposited onto the spacecraft's hull year after year. That energy shows up both as heat and as radiation damage, since each high-speed impact can knock atoms loose from the hull material, creating microscopic defects that accumulate over the years, gradually making materials more brittle and potentially damaging electronics. And that's just from neutral hydrogen. The interstellar medium also carries charged particles, cosmic rays, and Voyager measured cosmic ray intensity out there at roughly twice the level found in the inner solar system. These particles carry energies from millions up to billions of electron volts, far more damaging than ordinary thermal hydrogen impacts. A single high-energy cosmic ray can punch deep into materials, triggering cascades of secondary particles. Across decades of travel, that kind of exposure would add up significantly. Any humans aboard would need substantial shielding. Electronics would need to be radiation hardened. Biological samples would need dedicated protection. Voyager's measurements give future mission designers a genuine baseline for the radiation environment they'll need to plan around. The magnetic field measurements matter too, since charged particle trajectories bend in response to magnetic fields. The galactic field is weak, only about 50 nanotesla, but across truly vast distances, even a faint field like that can meaningfully deflect particles. For any spacecraft relying on a magnetic sail, a proposed propulsion concept that uses magnetic fields to interact directly with the interstellar medium, knowing that field strength and direction becomes essential, and Voyager's readings offer the first direct data on exactly that. The tsunami wave detections reveal something else worth remembering. Interstellar space isn't a still, quiet place. Shockwaves from solar storms travel billions of miles through it, and other stars almost certainly generate similar disturbances of their own. An interstellar spacecraft might well run into shockwaves originating from distant stellar outbursts, temporarily raising density or temperature along its path, or briefly boosting cosmic ray intensity. Understanding that the interstellar medium is dynamic rather than static matters enormously for planning any mission meant to last decades. The discoveries about the heliosphere's shape and size matter here too. Any spacecraft leaving the solar system has to cross the heliopause eventually, and depending on which direction it travels, the crossing might happen at 120 astronomical units, or 150, or well beyond. Knowing how far you'd actually need to travel before reaching true interstellar space matters enormously for mission planning. The heliopause also marks the last region where the sun holds any real sway. Beyond it, a spacecraft is genuinely on its own. Communication delays only grow more severe from there. At 120 AU, a signal takes nearly 17 hours to arrive one way. At 1000 AU, over 5 days. At a full light year, more than a year each way. The Oort cloud presents yet another challenge, a theorized shell of icy bodies surrounding the solar system, thought to stretch from roughly 2,000 astronomical units out to perhaps 100,000, nearly halfway to the nearest star. Voyager 1 won't even reach the inner edge of this region for another 300 years, and won't exit its outer boundary for some 30,000 years after that. Any interstellar mission, even one moving far faster than Voyager, would spend the bulk of its journey still technically within the Oort cloud, and therefore still within the Sun's gravitational sphere of influence. We simply don't know what conditions are like out there. Is the density of objects high enough to pose a genuine collision risk? Are there dust grains capable of damaging a high-speed spacecraft? Voyager won't be able to answer these questions. Its instruments will have long since gone silent by the time it reaches that region. But the simple fact that Voyager has now travelled for 50 years and still hasn't reached the Oort cloud offers real perspective. Our solar system is larger than we once assumed, and the journey to truly interstellar space is longer than we imagined. All of this paints a picture of interstellar travel as extraordinarily challenging, though not impossible, requiring technologies and capabilities well beyond anything we currently possess. Propulsion systems reaching a meaningful fraction of light speed, materials robust enough to endure decades of impacts and radiation, power sources capable of running for decades without any maintenance, communication systems able to send signals across light years, and navigation systems that can operate autonomously since round-trip communication delays make real-time control from Earth simply impossible. The Voyagers have shown us precisely what we're up against. They've measured the very environment we'd need to cross, and revealed that even our own local cosmic neighborhood holds far more complexity than we assumed. None of this means we shouldn't attempt interstellar travel. It just means we need to be honest about the scale of the challenge and the timescales involved. On February 14, 1990, Voyager 1 turned its camera around for one final look back at the solar system it was leaving behind. By then, the spacecraft sat about 3.7 billion miles from Earth, roughly 40 astronomical units beyond Neptune's orbit, still decades away from the heliopause it was slowly heading toward. NASA commanded the spacecraft to rotate its scan platform and capture a series of images, a kind of family portrait of the solar system, 6 planets in all: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was lost in the sun's glare, too close to photograph. Mars appeared too small and faint. Pluto was simply too dim to register at all. In one of those images, Earth shows up as little more than a single tiny point of light, a pale blue dot smaller than a pixel, suspended inside a stray beam of scattered sunlight. Carl Sagan, who had championed including cameras on Voyager in the first place and had worked closely on the golden record, saw that image and was moved to write one of the most enduring reflections on humanity's place in the cosmos. He observed that every person who had ever lived had lived out their entire existence on that single speck. Every war, every romance, every triumph and heartbreak, all of it unfolding on a mote of dust caught in a beam of light. From Voyager's vantage point, Earth carried no special significance whatsoever. Just one planet among several, smaller than Jupiter, dimmer than Venus, distinguishable only because we happen to know it's there, since we came from it ourselves. That image ties into Voyager's later discoveries in a quietly moving way. The very spacecraft that captured it went on to cross the heliopause, to enter interstellar space, to measure the galaxy beyond the reach of our own star. And from way out there, from genuine interstellar space, Earth becomes even less significant still. The entire solar system amounts to a small bubble adrift in the vastness of the galaxy. Our sun is just one star among hundreds of billions. The heliosphere itself is one modest region within the almost unimaginable sprawl of interstellar space. What the Voyagers uncovered reminds us that even our closest cosmic surroundings hold more complexity than we ever assumed. And if we're still learning basic facts about the boundary of our own solar system, it's worth wondering how much more remains to learn about the galaxy and about the universe as a whole. The pale blue dot image, in the end, is really a reminder of scale, of just how small we are and how recent our presence has been on cosmic timescales. Earth itself is 4.5 billion years old. Humans have existed for perhaps 300,000 years. Civilization, maybe 10,000. Space exploration, less than 70. The Voyagers launched 49 years ago. They've been traveling for roughly a human lifetime, and they've barely slipped past the edge of the solar system, sitting right at the beginning of true interstellar space, just beyond the heliopause. The nearest star, Proxima Centauri, remains 4.24 light-years away, some 73,000 years distant at Voyager's current speed. And the spacecraft aren't even pointed that way. They'll make their nearest approaches to other stars in roughly 40,000 years, and even then at distances well over a light-year. Genuine interstellar travel, actually visiting other star systems, remains far beyond anything we're currently capable of. The Voyagers are interstellar only in the sense that they've left the heliosphere behind. They now drift through the space between stars, but they aren't traveling toward any star in particular. They're simply drifting. And yet what they've achieved remains extraordinary. 2 spacecraft, built with technology from the 1970s, have traveled farther than anything else humanity has ever made. They've visited worlds no human eye had ever seen up close. They've crossed a boundary no spacecraft had ever reached before. They've measured conditions that had, until then, existed only as theory. They've shown us that the universe is always more intricate than our models suggest, that surprises are always waiting somewhere just past the horizon, and that exploration inevitably reveals things we didn't even know we were missing. The pale blue dot image captures that same spirit, looking back at where we came from with fresh eyes, recognizing both how precious that tiny world is and how small it truly is. Then turning around and continuing the journey outward into the unknown. By 2026, closing in on 50 years since launch, both spacecraft are still operational, which is genuinely extraordinary given they were originally built for a 5-year mission. They've lasted 10 times longer than their intended lifespan, but they are slowly and inevitably dying. The plutonium inside their generators keeps decaying. Power output keeps dropping, and there's no way to recharge or replace those power sources once they're spent. Voyager 1 currently sits about 159 astronomical units from the Sun, roughly 14.8 billion miles out, its signal taking more than 22 hours to reach Earth. Voyager 2 trails behind at about 132 AU, some 12.3 billion miles, with an 18-hour signal delay. Both spacecraft continue moving at roughly 38,000 miles per hour relative to the Sun, with Voyager 1 traveling slightly faster and consequently pulling farther ahead. Each year, Voyager 1 gains about 3.6 more astronomical units of distance, while Voyager 2 gains roughly 3.3. The power situation has become genuinely critical. As of 2026, Voyager 1 has only about 249 watts remaining, while its instruments and systems require roughly 245 watts just to keep functioning, leaving a margin of only about 4 watts. Every few months, engineers are forced to power down another heater or drop some system into standby mode just to keep the spacecraft running. The two probes are, quite literally, growing colder. Some instruments have already frozen solid and stopped returning data. Back in 2020, NASA switched off the heater for Voyager 2's cosmic ray instrument entirely, and its temperature plunged to minus 74 degrees Fahrenheit. Engineers fully expected it to fail. Instead, it kept working, 1970s-era engineering running 40 degrees below its intended operating temperature and still faithfully returning data. But time is genuinely running short. Somewhere between 2025 and 2027, there simply won't be enough power left to run both the spacecraft's core systems and any science instruments simultaneously, forcing engineers to begin permanently retiring instruments one by one. By 2030, perhaps 2032 at the very latest, the power budget will finally be exhausted entirely. The spacecraft won't have enough energy left to communicate with Earth at all. Their transmitters will fall silent for good. The Voyagers, though, will keep traveling regardless, still moving at 38,000 miles per hour. Since there's no friction out in the vacuum of space to slow them down, and nothing to stop them. They'll simply drift onward, year after year, decade after decade, century after century, carrying with them a record of the medium they helped us measure for the first time. The shock waves from solar storms, the shifting densities, the tangled magnetic structures, all of it continuing to unfold. Unwitnessed once their instruments finally go quiet, unrecorded because they'll no longer be able to communicate, but still happening out there all the same, still real. And they'll keep carrying their golden records along with them. sounds and images from a planet billions of miles behind them by then. Music and greetings drifting silently through the void. In roughly 40,000 years, they'll make their closest approaches to other stars, Voyager 1 passing within 1.6 light-years of Gliese 445, Voyager 2 within 1.7 light-years of Ross 248. Still more than a light-year from anything. Nowhere near close enough to call it an actual arrival, and nowhere near close enough for any gravitational interaction to occur, just passing through, in the vast emptiness between stars. The odds of anyone ever finding either spacecraft sit essentially at zero. Space is simply too vast, the galaxy holds hundreds of billions of stars, and the sheer volume involved is almost impossible to grasp. The Voyagers themselves are far too small, too cold, and too dark to detect from any real distance. And they aren't aimed at any particular star to begin with, they're simply drifting in whatever direction their final trajectory adjustments happen to send them. And yet they'll remain out there for millions of years, quite possibly billions, potentially until our own sun eventually burns out and becomes a white dwarf, until the galaxy itself has changed in ways we can scarcely picture today. Humanity's first true ambassadors to interstellar space, proof that a species that evolved on one modest little planet managed to build machines capable of leaving that planet entirely, leaving their home system and venturing out into the wider galaxy. Even if we never hear from them again, even if they never cross paths with another civilization, even if they eventually collide with something or fall into a star somewhere down the line, they will already have served their purpose. They explored the outer planets and rewrote our understanding of them. They crossed the great boundary and measured interstellar space directly for the very first time. They proved our models were wrong and that the universe holds far more complexity than we assumed. They proved that we can build machines sturdy enough to function in the harshest environment imaginable. Machines that outlast their design lifetime by a wide margin. Machines capable of venturing into the truly unknown and still sending knowledge home. And the discoveries they made, the data they gathered, the knowledge they handed us, all of that is permanent now. It can never be taken away. Each Voyager carries with it a golden record, a 12-inch gold-plated copper disc holding a carefully chosen collection of sounds and images from Earth. The record was designed to endure for billions of years in the vacuum of space, since gold doesn't corrode or oxidize, and there's no oxygen or water out there to degrade the metal in any way. The information itself is physically etched into the disk's surface rather than stored magnetically or electronically, its grooves carrying analog audio much like an old vinyl record. Though, instead of continuous music, it holds a carefully curated sampling of Earth's sounds, images, and music. Even if every electronic system aboard the spacecraft eventually fails, even once the power runs out completely, the record itself should remain intact and playable, assuming whoever finds it has the right equipment. The sounds chosen for the record were meant to capture something of Earth's diversity. Natural sounds appear first, wind moving through trees, rain falling, thunder rolling, surf breaking against a shoreline, the deep rumble and sharp cracks of a volcanic eruption, the low ground shaking sound of an earthquake. The haunting songs of humpback whales recorded out in the open ocean, calls complex enough to travel for hundreds of miles underwater, birdsong from a variety of species, the cheerful chirp of crickets, frogs croaking beside a pond, a dog barking. All of it meant to speak to the sheer biodiversity of this planet. Then come the human sounds, a baby's cry, that universally recognizable sound of new life beginning. Footsteps walking, laughter, both women's and men's, a heartbeat, the steady rhythm that keeps a person alive, the gentle sound of a mother kissing her child, sounds of tools in use, showing off human ingenuity, a hammer striking an anvil, metal against metal, a saw working through wood, the rasp of teeth cutting into timber, a tractor engine running steadily. Sounds of transportation follow, tracing human mobility across history, a horse pulling a cart, an ancient mode of travel, a train whistle marking the industrial age, a jet aircraft roaring overhead, and the thunderous power of a Saturn V rocket launch. The very kind of power that sent these spacecraft on their journey to the stars. Then there's the music, drawn from across the world and throughout human history. Perhaps the single most difficult part of the entire project to assemble. How, after all, do you choose music meant to represent the whole of humanity? The selection includes Bach's Brandenburg Concerto No. 2, prized for its mathematical precision and emotional depth. Beethoven's Fifth Symphony, among the most instantly recognizable pieces in Western classical music. Beethoven's String Quartet No. 13, more intimate and reflective. Mozart's The Magic Flute, blending drama with beauty. Stravinsky's The Rite of Spring, raw and groundbreaking. But the committee understood that Western classical music alone couldn't speak for everyone. So the record also includes traditional gamelan music from Java with its intricate interlocking rhythms. Music from Senegal, built on complex polyrhythms and call and response patterns. Pygmy music from what was then Zaire, now the Democratic Republic of the Congo. Aboriginal songs from Australia, among the oldest continuous musical traditions still practiced on Earth. Panpipe music from Peru echoing through the Andes, shakuhachi flute music from Japan, spare and meditative. Traditional Chinese music built on its distinctive pentatonic scales, Indian classical music with its intricate ragas and talas, American blues carrying the weight of pain and resilience, jazz featuring Louis Armstrong's unmistakable trumpet and voice, rock and roll through Chuck Berry's guitar work and lyrics capturing American teenage life, Georgian choral music rich with dense, layered harmonies. Each selection was chosen not merely to represent a genre or a culture, but to capture something essential about how humans express themselves. The selection committee, led by Carl Sagan, wrestled constantly with difficult choices. Every piece of music included, every sound chosen, represented thousands of alternatives left on the cutting room floor. There were disagreements, long debates, and plenty of compromise. Some committee members pushed for more contemporary pop music, while others felt classical compositions better reflected humanity's artistic achievements. Some wanted to include religious music, hymns, sacred chants, but which traditions should be represented? Christianity, Islam, Hinduism, Buddhism, countless indigenous traditions, and including any one risked seeming to slight all the others. The committee tried to balance genuine representation with artistic quality, striving to include voices from many cultures, even knowing that some would inevitably end up overrepresented and others underrepresented. How really do you capture the whole of human culture on a single disc? What deserves to be preserved? What would we even want an alien civilization to understand about us? The record also carries greetings in 55 languages, ranging from ancient Akkadian to modern English. Akkadian, a language extinct for thousands of years, stands alongside Sumerian, another ancient tongue from Mesopotamia, and Hittite, Latin, and ancient Greek. Modern languages spoken by billions round out the collection: Mandarin Chinese, Spanish, Hindi, Arabic, English, French, Russian. Each greeting runs only a few sentences, offering peace and friendship, greetings from the children of planet Earth, expressing hope that one day, having solved the troubles we still face, humanity might join a wider community of civilizations across the galaxy, and that this record stands as a symbol of our hope, our resolve, and our goodwill within a vast and remarkable universe. Similar sentiments echo across dozens of languages, each one emphasizing peace, friendship, and goodwill, a hopeful message sent out by a species still very much wrestling with war and division back home. Then come the images, 116 of them in total, encoded digitally onto the record. These aren't stored as ordinary pictures. Instead, each one is translated into a sequence of audio tones representing brightness values across each pixel, meaning the images exist as sound that can be decoded back into pictures. The disc includes mathematical and physical definitions meant to explain our scientific understanding, diagrams covering basic arithmetic, numbers rendered in binary, definitions of physical units like time, distance, and mass, chemical diagrams showing atoms and molecules, the double helix structure of Na, the molecule carrying genetic information for life on Earth, diagrams of atomic structure showing electrons orbiting a nucleus, a diagram of the solar system itself showing the sun and its planets, with Earth marked as the third one out, a photograph of Earth seen from space, the blue marble suspended in blackness, landscapes capturing Earth's variety, mountains rising toward the sky, deserts sculpted by wind into dunes, dense forested regions, oceans with waves rolling toward beaches. Images of human anatomy illustrating the structure of our bodies and of human reproduction, showing how one generation gives rise to the next. These particular images sparked real controversy among committee members. Some worried they were too explicit, though others argued that any sufficiently curious intelligence would need to understand basic human biology to understand us at all. The record also shows people from many cultures engaged in everyday life, a family sharing a meal together, children at play, athletes running and jumping, people at work. Architecture from a range of civilizations appears too: the Great Wall of China, the Taj Mahal, modern skyscrapers, and traditional houses from different cultures around the world. Images of food show what and how people eat. Paintings and sculptures represent human artistic creativity. Technology appears through images of tools, machines, and telescopes alongside a supermarket, illustrating the modern way we obtain goods, and a traffic jam, hinting at both the challenges of urban transportation and, perhaps, a quiet nod to human overconsumption. A page from Newton's Principia rounds things out, showing the mathematical laws that govern motion itself, These images were encoded using a method that would have felt familiar to anyone in 1977 who had seen early television or slow-scan video. Lines scan across the image, and the brightness at each point translates into an audio frequency. Any extraterrestrial civilization that eventually found the record would need to work out that certain stretches of audio actually encode pictures. Hardly an impossible task for a civilization already capable of retrieving a spacecraft from interstellar space. Clues toward this are etched right onto the record's aluminum cover, itself something of a marvel in information design. Pictograms on the cover explain how to play the record, specifying its rotation speed of 16 2/3 revolutions per minute. An oddly specific figure chosen for sound technical reasons, along with the correct positioning of a stylus needed to track its grooves. Additional diagrams show exactly how to decode images from the audio signal using binary representations of the timing and scanning parameters required to reconstruct each picture. The cover also includes a pulsar map, showing Earth's location relative to 14 distinct pulsars, rapidly rotating neutron stars that emit radio pulses at regular intervals. Each pulsar's period functions almost like a cosmic fingerprint, unique to that star. And by showing the periods and directions toward these 14 pulsars, the map effectively pinpoints Earth's location in both space and time. The very same map appeared on the earlier Pioneer plaques as well. Because pulsar periods slowly shift over time as the stars gradually lose energy, the specific periods recorded on the map also reveal roughly when the record itself was made. Putting the golden record together took an enormous collaborative effort. Scientists, artists, musicians, linguists, and anthropologists all had a hand in it. John Lomberg created many of its diagrams and images. Anne Druin helped select much of the sound and music included. Frank Drake designed the pulsar map. Linda Selzman-Sagan drew the human figures shown on the cover. The whole team had only a few months to finish the project, since the Voyager spacecraft themselves were being built on NASA's tight construction schedule, and the launch windows were completely inflexible, dictated by that rare planetary alignment. The record had to be finished, manufactured, and installed before liftoff. No exceptions. Technical limits shaped nearly every decision along the way. The total amount of data that could fit on a single disk was capped by groove spacing and the record's diameter. Audio quality had to be weighed against total playing time, since higher fidelity recordings simply take up more space, limiting how much could be included overall. Image resolution had to be balanced against the sheer number of images, since more pictures meant lower resolution for each one. Every choice involved some kind of trade-off. Every addition meant leaving something else out. In the end, the golden record amounted to more than just a scientific artifact. It became something closer to a philosophical statement, an honest attempt to answer some genuinely profound questions. What does it actually mean to be human? What should we tell another intelligence about ourselves? What's worth preserving for all of eternity? What manages to transcend our differences and speak to something we all share? There were plenty of disagreements along the way about exactly what music to include. Western classical music felt familiar to the committee, sure, but was it truly representative of humanity as a whole? Should pop music have a place? Rock and roll struck some cultures as controversial, and religious music raised the same unanswerable question: which religions exactly deserve inclusion? The committee tried to strike a balance between broad representation and lasting quality, choosing pieces they considered both aesthetically significant and culturally meaningful, working to include voices from as many cultures as they could manage, even knowing some would inevitably end up overrepresented while others were left thinner than they deserved. The images sparked similar debate. Some committee members wanted to include scenes of war, poverty, and disease, arguing that leaving them out would present an incomplete picture of human experience. Others felt strongly that humanity should present its best face to the cosmos, emphasizing achievement and aspiration instead. The final selection ultimately leaned toward the positive, while still including quiet hints of the challenges we face. Technical constraints shaped these choices too. The same trade-offs between data capacity, audio quality, image resolution, and sheer quantity running through every decision made. Carl Sagan and his team understood from the start that the odds of the record ever actually being found were vanishingly small. The Voyagers are tiny objects adrift in an unimaginably large volume of space. The galaxy alone contains hundreds of billions of stars, and the emptiness between them is almost impossible to comprehend. The odds that either spacecraft will ever pass close enough to another star system to even be noticed sit essentially at zero, and even in the unlikely event that one did drift near a star system, the odds that a technologically advanced civilization happened to be there at just the right moment shrink even further. Most stars, after all, don't host planets. Most planets that do exist aren't suited to life. Most life that does arise never develops intelligence. And most intelligent species, even if they exist, might never develop the kind of technology capable of observing or retrieving something from interstellar space. Realistically, the golden record is far more likely to eventually be destroyed than ever discovered. Across billions of years, the Voyagers might collide with something. A planet, an asteroid, even a stray dust grain striking at just the wrong angle could do catastrophic damage. They might eventually fall into a star. They might simply be worn down by radiation over spans of time we can barely conceive of. But the act of creating the record mattered deeply for us, regardless of whether anyone ever finds it. It forced an entire team of people to sit with the question of how they'd explain humanity to someone who knew absolutely nothing about us, what actually matters, what's genuinely universal, what manages to outlast any single culture or moment in time. The Golden Record captures a snapshot of Earth exactly as it was in 1977. Some of its languages have since gone extinct or nearly so. Some of its music is rarely performed anymore. Some of its images show things that no longer even exist. But it remains a kind of time capsule, a message sealed in a bottle and cast into the cosmic ocean. A quiet declaration that we were here, that we existed, that we carried thoughts and feelings and culture and dreams, and if it's never found, that's perfectly all right. The real value was always in the act of creating it, not in whether it's ever discovered, in sitting down and truly thinking through what matters most, what endures, and what we would want to say about ourselves if given just one chance. And now that record sits out there in interstellar space, riding along with Voyager 1, travelling at 38. Dawley 0 miles per hour through the very interstellar medium the spacecraft helped us discover in the first place, carried by a vehicle built by a species that has existed for perhaps 300,000 years, barely a blink on any cosmic timescale. In 40,000 years, when Voyager 1 finally passes within 1.6 light-years of Gliese 445, will any trace of human civilization still remain? Will Earth still be a place where life can thrive? Will we have spread out to other stars by then, or vanished entirely? Nobody can say. But the golden record will still be out there regardless, still intact, still carrying its quiet message, a testament to a moment when a young species looked up at the night sky and dared to send a small piece of itself outward into the unknown. The entire Voyager program, from its earliest planning through the Neptune encounter, cost roughly $865 million, which, adjusted across the decades, works out to several billion in today's terms. And yet spread across the full span of the mission, that's a remarkably modest investment given everything it returned. 4 planets studied up close. Dozens of moons discovered or examined in detail. The first observation of volcanic activity anywhere beyond Earth. The first real hints of subsurface oceans hiding beneath icy moons. The first measurements of the termination shock. The first crossing of the heliopause. The first direct sampling of the interstellar medium itself. Every modern textbook covering the outer solar system leans on Voyager's imagery. Every model of the heliosphere incorporates Voyager's data. Every serious conversation about interstellar space eventually references something the Voyagers found. These 2 spacecraft quietly rewrote our understanding of the solar system and the boundary that surrounds it. They showed us that Io is geologically alive, driven entirely by tidal heating, a discovery that reshaped how scientists think about what powers geology on other worlds. It isn't only radioactive decay buried deep in a planet's interior that can drive volcanism and tectonics. Tidal forces from gravitational interactions can do the same, a mechanism that applies not just to Io, but to Europa, to Enceladus, and potentially to exomoons circling giant planets around distant stars. They suggested Europa might be hiding a subsurface ocean, a possibility that has shaped decades of mission planning since, with future missions to Europa specifically designed to search for signs of life in those hidden waters. If life is ever found there, it would prove that life can emerge independently in more than one place, even somewhere as different from Earth as an ocean sealed beneath miles of ice. They revealed the astonishing complexity hiding within Saturn's rings, thousands of individual ringlets, shepherd moons, resonances, traveling waves, a natural laboratory for studying orbital mechanics and disk dynamics, whose lessons have since been applied to protoplanetary disks forming around young stars, to accretion disks swirling around black holes, and even to the structure of galactic disks themselves. They explored Uranus and Neptune, remaining to this day the only spacecraft to have ever visited either world. Nearly everything we know about their atmospheres, magnetic fields, and moon's traces back to Voyager 2's brief flybys decades ago. And then, after the planets, they simply kept going, through the heliosheath, across the termination shock, through the unexpected magnetic highway, and finally across the heliopause into interstellar space itself. They measured the distance to that boundary and found it sitting far beyond where anyone had predicted. They measured the heliosphere's shape and found it asymmetric rather than the tidy sphere everyone expected. They measured the properties of the interstellar medium directly and found them subtly different from every model. They detected tsunami waves from solar storms rippling outward through interstellar space. They measured the galactic magnetic field and found its orientation genuinely surprising. They mapped the directionality of cosmic rays and found patterns nobody had anticipated. Each one of these findings forced scientists to revisit their assumptions, revise their models, and reconsider what they thought they understood. This, really, is the quiet value of exploration. Not simply confirming what we already suspect, but uncovering what we don't yet know, finding the surprises, and learning again and again. That reality tends to be more interesting than our theories give it credit for. The Voyagers were built to explore the outer planets, and at that they succeeded completely. But their most enduring legacy might well be everything they discovered afterward. Clear evidence that we still don't fully understand even our own cosmic backyard. NASA is currently exploring a possible follow-up mission called the Interstellar Probe. It remains in the concept stage for now, with no confirmed launch date or budget secured, but its scientific goals are already clear to answer the very questions the Voyagers first raised. This probe would be designed from the outset for an interstellar journey, with more power, a longer working life, sharper instruments, and considerably greater speed. The goal would be reaching somewhere between 500 and 1,000 astronomical units within 50 years, 5 to 10 times farther than either Voyager has managed so far. Achieving that would require traveling at roughly 80,000 to 160,000 miles per hour, about twice Voyager's current pace or more, likely demanding either a far more powerful launch vehicle or a closed solar flyby paired with solar thermal propulsion, or some other advanced propulsion concept still being developed. Among its scientific goals would be a more detailed look at the heliosphere's nose and tail. Voyager 1 crossed near the nose, and Voyager 2 crossed closer to the side, but the tail itself remains largely unexplored. How far does it really stretch? What does its structure look like? The interstellar probe would also survey the outer heliosphere far more systematically than Voyager's single-point measurements along two narrow trajectories allowed, mapping how conditions vary across distance and direction and pushing much farther into the interstellar medium itself. Even 500 to 1,000 astronomical units remains extraordinarily close to the Sun on a galactic scale, but it would be far enough to reveal whether the properties Voyager measured hold steady or whether they shift significantly across greater distances. The mission might also search for the heliopause's predicted bow shock, thought to exist somewhere between 140 and 230 astronomical units. Though given how far off the models were about the heliopause itself, that bow shock could genuinely be almost anywhere. The interstellar probe might locate it, or it might not. Either outcome would carry real scientific value. Such a spacecraft could carry advanced particle detectors to better characterize galactic cosmic rays, magnetometers to map the structure of the galactic magnetic field, and plasma wave instruments to detect turbulence and waves rippling through the interstellar medium, possibly even a camera capable of photographing the solar system from outside its own boundary. A kind of family portrait taken from interstellar space itself. But this mission remains decades away. Design work continues quietly, funding hasn't yet been secured, and even under the best possible circumstances, launch likely wouldn't happen before the 2030s, with the spacecraft not reaching 500 astronomical units until sometime in the 2080s. Many of the scientists currently designing this mission probably won't live to see its primary results come back. This is simply the nature of interstellar exploration. Its timescales stretch well beyond any single human lifetime. The Voyagers themselves launched before many of the scientists now analyzing their data were even born. The engineers currently maintaining the deep space network weren't alive when these spacecraft were originally built. Whoever eventually receives the Voyager's very last transmissions is likely still in elementary school today, or not yet born at all. Science operating on these timescales demands institutional patience, continuity passed down across generations, and a genuine willingness to start projects whose conclusions we personally won't live to witness. But that, in a sense, is simply what exploration has always required. Lewis and Clark charted the American West, yet full settlement took generations to follow. Magellan's expedition circled the globe, though Magellan himself died before the voyage was complete. Apollo landed humans on the moon, and yet we haven't returned there in over 50 years. Progress rarely moves in a straight line. It comes in fits and starts, bursts of rapid advancement, followed by long stretches of consolidation, sometimes even retreat. The Voyagers represent one particular moment in that larger story. A moment when funding happened to be available, technology was just barely adequate, the planets had aligned favorably, and the institutional will existed to attempt something genuinely unprecedented. That kind of moment may well come again. The interstellar probe might eventually launch. Humanity might send more spacecraft out into the interstellar medium, or it might not. The Voyagers may remain for decades or even centuries to come, the only spacecraft to have directly sampled interstellar space. Either way, what they've already discovered stands on its own. The data exists, the measurements are recorded, the surprises are documented for good. Future missions will build on everything the Voyagers learned. And even if no follow-up mission ever materializes, the Voyagers have already accomplished something permanent. They showed us what waits at the edge of the solar system, out in the space between the stars. They showed us it's stranger, more layered, and more dynamic than we ever assumed. And they showed us, gently but clearly, that we still have so much left to learn. Tonight we wandered through the quietly astonishing discoveries Voyager made out at the edge of the solar system. 2 spacecraft, launched back in 1977, carrying computers less capable than a modern calculator, built to last just 5 years, and yet still working nearly 50 years later. They visited Jupiter and witnessed volcanism firsthand on Io, the very first active volcanoes ever confirmed beyond Earth. They saw Europa's cracked icy surface, hinting at a hidden ocean underneath. They discovered Jupiter's own faint ring system. They visited Saturn and revealed thousands of individual ringlets woven through its rings. They studied Titan's remarkably thick atmosphere. They measured magnetic fields and radiation environments in detail. Voyager 2 went on to visit Uranus and Neptune, remaining, even now, the only spacecraft ever to reach either world. It photographed Miranda's strange, fractured terrain, It discovered Neptune's great dark spot and measured winds exceeding 1,100 miles per hour. It studied the geysers erupting from Triton, one of the coldest surfaces anywhere in the solar system. And then, having finished with the planets, both spacecraft simply kept going, out toward the edge. They crossed the termination shock where the solar wind finally slows. They passed through the heliosheath, that turbulent boundary region. They discovered the magnetic highway, an entirely unexpected structure nobody had predicted. Voyager 1 crossed the heliopause on August 25, 2012, at 121 astronomical units, far beyond anything the models had forecast. Voyager 2 crossed on November 5, 2018, at 119 astronomical units. They found that the heliopause sits nowhere near where we'd calculated, some 2.4 billion miles farther out than predicted. They found its shape genuinely asymmetric, nothing like the tidy, symmetric bubble scientists had expected. They found the transition itself layered and complex, marked by oscillations and structures nobody had anticipated. They measured the interstellar medium directly for the very first time. Its density, temperature, and pressure all subtly different from what the models had forecast. They detected tsunami waves from solar storms rippling outward through interstellar space. They measured the galactic magnetic field and found its orientation different from what anyone expected. They mapped cosmic ray intensities and uncovered asymmetries that revealed genuine structure within our local interstellar surroundings. 7 major discoveries in total. And every single prediction turned out to be wrong in some way. Though not completely wrong, the basic picture held up reasonably well. But every specific detail, every number, every quantitative forecast missed the mark. This is precisely what exploration does. It tests our understanding against reality, and reality, it turns out, is always more intricate than our theories anticipate. The Voyagers taught us something valuable about humility. We believed we understood the edge of the solar system. We built sophisticated computer models. We ran simulations for years on end. We made confident predictions about exactly where the boundary would sit, what shape it would take, and how the transition would unfold. We wrote it into textbooks, drew clean, spherical diagrams of the heliopause, and published papers calculating the precise distance at which Voyager would eventually cross. And then 2 actual spacecraft went out there and measured it directly, and we discovered we'd been wrong about nearly everything, though not fundamentally wrong about the underlying physics. The basic picture held. Solar wind really does meet the interstellar medium, a boundary really does form where their pressures balance, and cosmic rays really are more intense beyond that boundary. But every specific prediction, every measurable detail, turned out to be off. The distance was wrong by billions of miles. The shape was asymmetric where we'd expected symmetry. The transition unfolded over years where we'd expected mere weeks. The magnetic highway wasn't predicted at all. The properties of the interstellar medium didn't line up with our estimates. The orientation of the magnetic field caught everyone by surprise. The directionality of cosmic rays didn't match what anyone had anticipated. 7 major discoveries. 7 separate ways that reality quietly outpaced our very best theories. This is simply how science actually works, not the neat linear progression so often portrayed in textbooks, not a tidy straight line from hypothesis to confirmation, but a genuinely messy process of prediction, measurement, surprise, and revision. We build models from the best data available. We make predictions. We test those predictions against reality. When reality doesn't line up, we learn something new, refine our models, and go on to make fresh predictions to test all over again. The Voyagers embody this process perfectly. Scientists made honest, careful predictions grounded in solid physics and the best data they had. Those predictions turned out to be wrong in meaningful ways, not because the scientists were careless or mistaken in their reasoning, but simply because the universe holds more complexity than any single model can capture. There were factors nobody had accounted for, properties of the interstellar medium that had been estimated slightly incorrectly, dynamics at the boundary nobody had anticipated, and entirely new phenomena like the magnetic highway that no one had ever imagined could exist. And that's perfectly all right. That's simply how we learn. The predictions that turned out wrong weren't failures. They were opportunities, chances to discover something genuinely new, to sharpen our understanding, and to build better models for whichever spacecraft come next. The two spacecraft are dying now, slowly and steadily. The plutonium inside their power generators keeps decaying, their output falling by roughly 4 watts every single year without exception. Instruments are being retired one after another to conserve what little power remains. Heaters are switched off, letting entire systems slowly freeze. Backup systems activate as primary ones fail. Engineers perform a kind of ongoing triage, deciding carefully what to preserve and what to let go. By 2030, perhaps 2032 at the very latest, there simply won't be enough power left. The transmitters will fall silent for good. The final signal will fade quietly into the cosmic background noise, and the deep space network will no longer hear anything at all from that particular point in the sky. But the spacecraft will keep traveling regardless, still moving at 38,000 miles per hour, forever, since there's no friction out in the vacuum of space to slow them, and nothing there to stop them. They'll simply keep drifting outward, year after year, decade after decade, century after century, moving through the very interstellar medium they helped us measure for the first time, past shockwaves born of solar storms and stellar outbursts, through shifting densities and tangled magnetic structures. All of it still unfolding, unwitnessed now, because their instruments have finally gone dark, unrecorded because they could no longer send anything home, yet still happening out there all the same, still entirely real. Still carrying their golden records loaded with sounds and images from a planet now billions of miles behind them. Bach and Beethoven and Chuck Berry drifting quietly through the void. Greetings in 55 languages that no one will ever hear. Images of Earth, of people, of our entire solar system that no one will ever see, unless, against almost impossible odds, they someday cross paths with another civilization. In roughly 40,000 years, they'll make their closest approaches to other stars, Voyager 1 passing within 1.6 light-years of Gliese 445, Voyager 2 within 1. 7 light-years of Ross 248, both still more than a light-year from anything at all, nowhere close enough to say they've truly reached another star system. Nowhere close enough for any real gravitational interaction, simply drifting past through the vast emptiness that separates the stars. The odds that anyone will ever find them sit essentially at zero. Space is simply too vast. The galaxy alone holds hundreds of billions of stars. The volume of space involved is almost impossible to hold in mind. The Voyagers themselves are too small, too cold, too dark to detect except at extremely close range, and they aren't even aimed at any particular star. They're simply drifting in whatever direction their final trajectory corrections happened to send them. And yet they'll remain out there for millions of years, quite possibly billions. Potentially until our own sun eventually burns out and becomes a white dwarf. Until the galaxy itself has changed in ways we can scarcely imagine today. Humanity's first true ambassadors to interstellar space. Proof that a species that evolved on one modest little planet learned to build machines capable of leaving that world behind entirely. Leaving their home system and venturing outward into the wider galaxy. Even if we never hear from them again, even if they never encounter another civilization, even if they're eventually destroyed in a collision or drawn into a distant star, they will already have served their purpose fully. They explored the outer planets and transformed our understanding of them. They crossed the great boundary and measured interstellar space directly for the first time in human history. They showed us our models were wrong, and that the universe holds more complexity than we ever assumed. They proved we can build machines capable of enduring in the harshest environment imaginable, machines that outlast their intended lifespan many times over, machines capable of venturing into true uncertainty and still sending knowledge back home. And everything they discovered, all the data they returned, all the understanding they gave us, that remains permanent. Nothing can take that away. Future missions will build on everything Voyager learned. The interstellar probe, should it ever launch, will lean on Voyager's discoveries to plan its own trajectory and design its own instruments. Future textbooks will cite Voyager's findings about the heliosphere and interstellar space for generations to come. Future scientists will keep studying Voyager's data for decades yet, likely uncovering insights we haven't even noticed. The measurements themselves live on in NASA's archives. The images remain stored and safely backed up. The knowledge has already been woven into our broader scientific understanding. The Voyagers showed us the edge of our solar system, and in doing so, showed us that even at that edge, even at a boundary we once thought we understood completely, reality remains stranger and more wonderful than we ever imagined. They showed us that exploration is never just about confirming what we already believe. It's about discovering what we don't yet know, chasing down surprises, and learning over and over that our theories, however sophisticated, are always just approximations of a far more complex reality. They taught us humility in the face of the universe, showed us that we're still learning about our own cosmic backyard, still uncovering basic facts about where our solar system quietly ends and interstellar space begins. And if we're still learning that much about our own doorstep, just imagine how much remains unknown about the wider galaxy, and about the cosmos as a whole. 2 spacecraft, built with technology from the 1970s. Computers holding less memory than a microwave oven. Transmitters weaker than an ordinary light bulb. Power systems running on nothing but radioactive decay. Traveling now for nearly 50 years. Still teaching us. still quietly surprising us, still showing us that the universe is far more interesting than we ever gave it credit for, until the day they finally fall silent and drift off into the eternal night, carrying their message onward toward the stars. A message from a species that dared to explore, that dared to send a small piece of itself out into the unknown, that dared to wonder what lies beyond, and found answers stranger and more wonderful than anyone could have predicted. So, as you drift off tonight, maybe let your mind rest on this. 2 small machines, built by hand half a century ago, are still out there right now, quietly sailing through the space between the stars, carrying a golden record and a message of peace toward a destination they'll never truly reach. If tonight's journey helped ease you towards sleep, a like or a subscribe helps this channel keep bringing these quiet cosmic stories to more curious minds. No pressure at all. Sleep well, and we'll wander somewhere new among the stars again soon.